Today I'm going to talk about my own project called Reactor, and also an initiative we launched with a few friends like TypeSafe and Red Hat and Netflix as well. And this initiative is called Reactive Streams. The use case I want to explain specifically about Reactor and Reactive Streams is the microservice. You know, this buzz bingo word we currently using a lot. And I think, in fact, microservice architecture and the reactive programming are tightly closed. So there we go. We have 40 minutes. I hope I'm not going to delay you from the lunch. I'm myself starving a lot, to be honest. So let's skip the ego part. Well, the thing is, the irony is I'm going to talk about microservices, but I'm not fancy about microservice word, to be honest. And that's why every time I'm going to mention it, I will try to use another qualifier like a nano service or not too big service or microservice. No, not this one. So what's a microservice? So microservice can be something very simple, and you will recognize a few of these examples, in fact. So that's an example of microservice, basically. It's quite simple, I know. But still, a microservice can be as simple as that, a Unix chain of commands. But everyone knows microservice more under this form, under this shape. So someone is posting, for instance, on a fictive site called dogecoin.money, and behind this request, we have someone, some services calling another application with a get, for instance, and another one aggregating these two responses inside a single application. Yeah, well, of course. Who knows? So we aggregate a few responses. We call a service behind this one is calling two other service. That's a classic form we know, microservice, the microservice architecture, you know, hexagonal architecture. And also it can be at a very, very small level, at very low level, in fact. It can be, for instance, a service. So I'm taking an example in Java or Groovy or Scala, whatever. For instance, this one is a service call to authenticate someone, and behind it will call two other services like hashing password, of course, not for the NSA, and find by name and hash to find eventually in a database. So all these examples have something in common, in fact. They do have a boundary. That's, in fact, microservice is just an attempt to say, okay, we have a boundary between few things calling each other. They synchronize each other to do something. And the problem is, because there are things interacting each other, either with a service or either the user himself is going to interact with your service. The problem is, the more you have boundaries, the more a locking thread is going to kick in. And it's called latency. And you know what? No one is really liking the action of knowing nothing, like waiting. But in fact, neither do the machines, because what happens if the machines wait for someone to reply? Well, a lot of things, actually. And because I want to try to be concrete about what happens, I focus on the revenue things. It's very important. In the end, what we try to do is, for our own companies, trying to make some money, and we want to have revenues. But the latency is the nemesis of that. Why that? Because, you know, a user waiting for your application to reply is someone potentially going away because he doesn't want to wait that much. And a lot of studies actually benchmark this wait and say, okay, after 5 seconds wait, the user, 50% of the user are going away, and this is translated in loss of revenues. Also, the fact that your services, so the machine-to-machine talk, the fact that services can wait between each other are compounding inefficiency. Why that? Well, the thing is, if your service waits for another one, it can't serve upstream service because it's already blocked waiting for another service. And that's really inefficient. And if you talk about, for instance, deploying on Amazon, what you're going to do in that case? Well, you're going to scale out, and scaling out is going to cost you so much money, especially on Amazon. So that's a main issue about microservice architecture or nanoservice architecture. The thing is, you don't want basically latency, or you want to fight it. You want to be more responsive. So in the end, the massive loss of revenue is going to probably come from your team itself, in fact, because the team is going to be pissed off by having created a boring application, and your turnover will increase, blah, 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 and the people leave, etc. It costs a lot of money, even softly. Anyway, what we come up with since at least for probably a decade now, but it's, you know, in computer sciences, everything is just everything has a new name for something existing 4 years ago, and reactive programming is one of those things. I often name it event-driven programming, in fact, because I don't see that much change, but we all need sometimes to increase adoption, kind of new branding, so that's what happens. So that's a possible answer to this issue. It's not a silver bullet, and people before me and people after me will explain that clearly, in fact, in detail. So the reactive programming picture, as advertised, especially by our lovely friends at TypeSafe, is simply something that is event-driven. Event-driven leads to fault tolerance because event-driven is about attaching dynamically consumers, and if one consumer fails to reply to one request, it's not such a big issue because a consumer is bulkheaded, in fact, is siloed, and if it fails, the other consumers won't fail, so that's the fault tolerance part. The other part is the scalability, because you can add more consumers if you have an event-driven application. You know, you listen to a topic, for instance, and you add more consumers because you want to consume more at a single time. Well, you can make it more scalable in theory. You can make it more elastic. And the two things lead, in theory, to low latency. So how so? Because if you have an event-driven application that is fault-tolerant, first you at least prevent your application you prevent your user to just wait for your application to restart, for instance, if something fails, because the error was constrained, siloed into a consumer. The other part is because it's scalable in theory. Normally your application is more responsive because it is able to just reply more quickly. There are other consumers available for your request, your incoming request. So that's the big thing about the reactive architecture. It must be resilient just to make sure that we achieve error bulkheading. And also, it must be scalable. It must be able to scale up transparently, and it must be able to scale out transparently, so distribute over nodes. But before going on to other nodes, make sure you use at least your CPU efficiently. So going back to Reactor, so one of the things Reactor offers is a solution to fight the latency. It's not a silver bullet, as I said before, but we try to fight that. That's our main concern. And to do that, we feature a set of asynchronous dispatches. So think about schedulers or thread manager. And these asynchronous dispatcher have a lot of, in fact, we have a few ones. And the main one we use to do real fast data ingestion is called ring buffer, disruptor ring buffer. We use LMAX disruptor, a very interesting hometown, in fact, framework we use at the very core of Reactor. And that allows us to do very fast message passing between one thread and another one without contention, without locking. That's another important point about reactive as well. So Reactor is divided in two main things, a kind of event bus where you can attach selectors, topic selectors. You know, if you know RabbitMQ, for instance, it's very similar. You create selectors, you notify these selectors, and something consuming of these selectors is going to react. So that's the event bus part. We have a class called Reactor, like Reactor framework, and that exactly does that. And the other part we do is the stream and the promises, which is also quite fancy buzzword we are currently facing these days. And the streams and promises are really interesting for a few things. unlike the event bus, you can, so you know an event bus, you attach to a selector, it's not really typed. You don't know exactly that, you can know, you can infer the type, but not necessarily exactly, because there is a level of indirection. We don't know, the event bus can be distributed, for instance. We don't know for sure that the object is the same when you notify it as when you receive it. It can be on another node, for instance, that it can have been serialized or this kind of thing. Stream and promise are actually different because they are type-checked flows, and we see that. And these two things are based on few artifacts, functional artifacts, because it's important to use, well, functional programming is by nature reactive for a few reasons. Because first, functional programming language is stimulus-based, so this is quite a good tool for anything reactive. And the functional artifact we use, for instance, is, we call that in Java, I don't know if we call the same in all the languages, to be honest, but in Java we call that single abstract method, artifact, components. For instance, a class that only has a single method. And with Java 8, it takes a lot of importances. And we see also as well that stream coming from Java 8 are using a lot of these single abstract method classes. The tuples is just a version of CSV, basically, a type-checked CSV. And the timers are, you know, very important in functional programming anyway, because we schedule things, and sometimes we need to schedule things ahead of time, and the timer is there for that. And in parallel of this thing, Reactor is based on a few tools you can use. You can pick them as much as you need them. So we classify them in two categories. We have what we call the fast I/O tools. So all the things to manage buffer, byte buffers, and all this kind of thing. Persistence queues, we use framework, for instance, called Java Chronicle, which is a very fast direct memory mapping to the file system. If you want to persist your messages, for instance, during event distribution. And the other thing we have is the fast data part. So we have kind of batch processing components. We have also allocator to pre-allocate the message envelope, because everything has a cost when you deal with asynchronous programming, including the message passing, as I mentioned earlier. So allocators, for instance, is really important if you don't want to pay at runtime the cost of creating a message envelope, an event message type, for instance. You would just want to pre-allocate them and feed them with the data input you want. In fact, we use a lot of the ring buffer patterns inside the framework itself, inside Reactor itself. Ring buffer does the same. It pre-allocates a lot of slots for your message passing to accelerate, to make it more fast. So let's go into the stream part. We have what we call a stream in Reactor, and this is just a simple example to start with. I think we recognize this kind of notation across a lot of languages today, and a lot of frameworks as well. In Java, I would say the main one doing this kind of thing is RxJava, a very good framework for streaming APIs. So what we do in this case, so I wrote in Groovy because otherwise it doesn't fit in a slide. I wrote in Groovy this thing. So the first thing we do, we create a stream. We access a kind of static method to just build a kind of factory. We create a stream. This stream is something you can attach a lot of operation. You can chain operation on it. So the first thing happening is the first step. What we do is map, or we can call that transform operation if you want to. So this thing is going to accept a name, for instance, and create a tuple of this name, plus something I add as a second column called servo, another string, in fact. The second operation, second step, you see they flow nicely, is another operation accepting, in that case, the previous result from the first step. So it's accepting a tuple. And in fact, it creates another tuple, but it takes the name from the first tuple. And we also, there is a slight mistake. I would have used tuple.t1.tuple.name, unfortunately. So I used the colon, in fact, to extract the information from the tuple. And the last step is what we call a terminal callback. To trigger this world chain, we need to use one of these terminal callback. In that case, for instance, it's a consume operation. Consume is going to be a file host, keeping consuming from your stream, anything happening. So you have a kind of flow, type check flow in there. How do you trigger it now? There are multiple ways to trigger it, but one of the simplest ways to trigger it is just to send some data using broadcast next. And you send that to the head of this pipeline, and basically the consume operation is a tail of this pipeline, and we consume everything, but all operations in the chain are going to be triggered. So that's the simplest stream you can ever do. So when do you use a stream? A lot of use cases, in fact. We use a lot for metric. We use a lot of streams mainly for two use cases, to be honest, or out of these 6 use cases I present here. The metric statistics are really important because streams libraries like us or RxJava come up with a lot of statistics, interesting method for statistics like sampling, like aggregating, like reducing operation accumulator to do counters and all these kind of things interesting in metrics. And the other use case we use a lot, streams and observable, if we talk about RxJava, is the micro-batching. Micro-batching is such a big topic nowadays as well. If you want to do micro-batching, this kind of approach is really interesting because you can aggregate incoming events using aggregate operation, like buffering operations. And once you get this accumulated state, you can serialize it in one go, which saves you from a lot of I/O cost. And we all talk about making that fast. So a stream is exactly what maybe you think it should be. A stream of data is just a sequence of data. Not necessarily finished. It can be unbounded, but it has the option to be bounded as well. Also, a stream is something that, well, as you've seen just earlier, enrich, filter your incoming events. And a main confusion we have, especially for the Java 8 programmers, a stream is certainly not a storage. So a stream is a kind of stateless object, maybe like an actor sometimes, in fact, or a stateless actor, because we have, we don't, unless you use the buffering operation, we don't keep the data, it just keeps flowing, and the operation reacts to the incoming event in chain. So we don't store this data. It's important because you don't want your memory use to increase like crazy. So the main difference between an event bus and a stream, at first, they work great combined. For instance, you create a topic. You can use, for instance, RabbitMQ. It's not necessarily tied to Reactor. You can use RabbitMQ to scale out your operations, but your RabbitMQ consumers can be all streams, and they receive the incoming event from RabbitMQ, and they do whatever they want to do, and they consume basically the event coming from RabbitMQ. The difference also is the publisher subscriber is really controlled in that case because, well, your producer has fully access to the stream. He knows the reference to the stream. It's type checked. And for instance, you won't use a reply to pattern if you want to do something after something happened. You just chain the operation. Reply to doesn't exist as such in a stream. You just add the operation if you need to add operation. So that's very interesting, in fact, because you can bound the stream. You can bind the stream to a request, to a user request. We'll see that. A very important thing, and that comes from the specification, a stream is thread safe because it doesn't accept signal concurrency. So a stream accepts events, but it doesn't accept concurrent events. If you want multiple, if you want concurrency, basically, you need to have multiple streams. But a stream is a lightweight object, so you won't be afraid to create multiple streams to parallelize or increase your concurrency, in fact. So one of the rule of thumb we come with is, in fact, if you event-driven application has more than 2 levels of nested composition, well, switch to stream because it's much easier to read. And that's, well, you know, I think we call that the cold block hell. And once you get in that, you just want to wake up, basically. And Another main difference we have in the stream API, in the stream wall, is the differentiation between hot stream and cold stream. So streams have mainly two different flavors. They can be really event-driven. Remember the first example I showed you? I broadcasted a signal myself manually. That's an hot stream because the consumer doesn't know when it's going to arrive, and he can't replay it. Once you broadcasted the event, it's going to be consumed. End of story. So a few examples of that is a trade, for instance, mouse click, a lot of reactive extensions, in fact, coming from Microsoft, are used in UI design because they use that for filtering mouse click, for instance, avoiding overflow of keystrokes, and this kind of thing. WebSocket is another example of hot stream, and that's really useful example as well for the hot stream. The cold stream, in the other hand, is something that you can replay because you have access to this thing stays in memory or is held somewhere, in fact. So you can replay it. If you attach a new consumer, you start from start. You restart from the very beginning. So that's the case of a file. If you attach a new consumer, you will consume everything from the file if you want to. Or it can be a computation result. So at some point, it will finish, but once it's finished, you don't need to re-execute it again, so the result can be stored. That's an example of cold stream. And in Reactor, you know, an example of a simple cold stream is just like that. In fact, you create a stream from for instance, in the case of iterable cold stream, if you want to create a stream from a collection or iterable, you just take a few elements. But after that, if you want to filter this, you can add an operation called take. It's a very common name for this kind of operation. Observable use the same. Microsoft use the same in their own reactive extension. It does what it says. You just want to take the first element of what you pre-created, the list of 5 elements. And in the end, if you want to attach a subscriber that does something with what you have created, you can do that. So it's a Java 8 notation. I use the method handler. But you can subscribe an object, a consumer, or whatever. We can use Groovy, for instance, or Scala. It doesn't matter. But that's the reactor, basically, the reaction of your stream, which will only react 3 times in that case. And after that, will complete. End of the story. If you want to do it again, you subscribe a new consumer. And also, we're working on this thing, for instance, for RabbitMQ. If you want to consume a queue with a stream, that's the kind of notation we use. That's an example of hot stream because you don't know when an event is going to reach you. It's completely decoupled. You consume RabbitMQ, so anything can trigger a message to an exchange that will trigger the queue. So I consume a queue. I tell it to dispatch on a specific scheduler, on a specific dispatcher. I use an environment for that. It's something tied to Reactor. And if nothing happened for the 31st second, I will just trigger an exception. I will just terminate the flow. So you can also bind your stream to a time limit. And in asynchronous programming, binding in size or creating a limit on size or creating a limit on time is really important. So. And after that, you subscribe everything coming from your RabbitMQ, for instance. So it takes just 4 operations to just consume something from RabbitMQ. I will deploy that very soon. I use my customer work to do a lot of these things. Basically, I oversell what I can, so I have more time to work on my open source stuff. But we all have all patterns to work overnight or work on a customer budget. Anyway, I'm going to deploy that very soon. And so coming specifically to the reactive stream specification. So what is a reactive stream doing with this reactor stream? So basically, reactor stream implements this specification called reactive streams. And reactive streams is defined as the specification define it, is just an async non-blocking data sequence. So that's clearly defined. We all have to be, if we implement the specification, we all implement an async non-blocking data sequence. Another requirement for anyone implementing this specification is it has to be very lightweight. It has to be embeddable. It doesn't have to consume so much memory. For instance, if you see that Reactor increase your heap memory use for, I don't know, doing nothing for 100 megabytes, well, it's quite easy in the JVM, to be honest. But anyway, if it does something that you didn't expect in terms of memory use or CPU use, we didn't reach that goal. And we can't claim with reactive stream implementation. It has to be interoperable as well. It's very important. So the story as well behind the reactive streams is we want to talk each other with the other framework. For instance, reactive stream in Reactor can talk to Akka stream or RabbitMQ streams or RxJava observable. They all talk each other because we implement all the same specification, or we try at some point. And it also has to be, that's in fact the main thing about this specification, it has to be, it has to embed a flow control, tight flow control operation. So let's see how it goes in fact. So in reactive streams, we define two artifacts, one called, in fact, 4 artifacts, but the main one are publisher and subscriber. I think that talks to everyone. And what does a publisher? It sends event to a subscriber. And what does a subscriber? That's the interesting part of this thing, because otherwise it wouldn't be very different from what we know until now. It does send what we call the demand. And signaling the demand back to the publisher allows for controlling the back pressure. And that's really the thing about the reactive stream specification. Because what happens is, if your consumer signal less demand than the publisher, in fact, is producing data, the thing is, we have an automatic buffer control kicking in. So if you have a slow consumer, we will start queuing operations to a certain limit defined, in fact, in advance. But if your consumer is faster than your publisher, it's never going to reach out to the queue. It's just going to go fast directly as a push operation to your consumer. And that's the difference, because a lot of things exist nowadays to do event-driven programming. But we've seen, in fact, in a few examples I'm coming with on Java 8, on RxJava, you don't have the choice. It's either one or the other. You either push or you either pull. And this difference exists because we don't have we don't have a specification to talk each other to say, okay, if you want to propagate back pressure, how I'm going to handle it. Now we have a kind of framework to propagate this back pressure to all of these technologies I've mentioned earlier. And we can also, because we know the volume, so a subscriber will never receive more than he has asked for. So we can scale dynamically. The producer basically can say, okay, this one is asking so much data, I'm going to ask for another subscriber to start consuming. So you can do this kind of load balancing very, very smartly. And in fact, that allows us to do this kind of thing. You can have publisher publishing to one subscriber fast and another one slowly, because the other one will have its own queue, its own mailbox to queue the event in case they are super slow. But the fast one is going to be super fast every time because they're going to be pushed every time. It will have the capacity, in fact, to consume them. Well, and what is in the data sequence? Basically, what you can guess. If this was an hot stream, you will only receive the event after time t you start consuming. If it's cold stream, you can be subscribed since the beginning. The reactive stream, by the way, doesn't define transformation. So it just defines the boundary between the publisher and the subscriber. It's just a set of 4 interfaces in Java. And we already think about implementing it on top of TCP protocol, because we work with Kazin, for instance, to see if we can implement this back pressure beyond the Java. We want to do that in all the frameworks, in all the languages, in all the technologies, because the more you have back pressure ready operation in your chain, well, the more you control the latency to the end, in fact. And that's very interesting because, for instance, if your database was not ready to send back data, because, in fact, your end consumer, which is a user, for instance, consuming off WebSocket, wasn't ready. He was already rendering something, a graph, a map, something. Well, the database is not going to send anything, so you save operations, you save CPU, and you save money in that case. So that's why we have also done this specification to be everyone to implement this specification to propagate the back pressure nicely from the more downstream to the most upstream. But I would say there is the Java 8 streams. What's a differentiator? Well, the Java 8 stream is basically a very nice technology for the staging operation. Unfortunately, it doesn't have this back pressure handling, and we talk about introducing that in Java 9. So we work with Doogly, who's behind the thread executor model in Java. Also, or you can see in this example of Java 8 streams, it's either one way or the other way. You prepare a call stream from a list, an array list, for instance, and as soon as you attach your operation, they are pushed. In fact, they're consuming what you're doing. And .sum, for instance, in that case, is going to be a pull operation. But you can see there is no dynamic change. In fact, it's either one or the other way. And what about these guys, you know, all these IPs are using RxJava, which is a great framework, to be honest. Well, you know, they provide the famous reactive extension coming from Microsoft, as I said earlier. Very recently, they've introduced the implicit back pressure support, so in 1.0, and they have a flexible scheduling, and they already have this kind of event-driven passing with a boundary like on next. And if you have a terminal state, for instance, an error state or a complete state, it's already existing in RxJava. And that's an example of RxJava. Instead of stream, they use observable with a call stream, some push operation, and as soon as you subscribe, you demand all data. That's changing. But these guys have joined the specification. So who's behind this specification? In fact, we're not alone, and a specification will never work if no one was joining, in fact. So TypeSafe, Oracle, because Doogly is working with us. No, Doogly is separate from Oracle, sorry. But Oracle is also interested because they want to introduce that in Java 9. And Pivotal, my own company, and Netflix, and a few other, in fact, Red Hat, Kazin. You recognize his name, even Twitter, because Storm is maybe going to be also an early adopter. And what does it allow us to do? Very interestingly, we can do all this nice connection between each other without bridging ourselves manually, because we all talk the same language. They implement subscriber interface, we implement subscriber, we implement publisher, basically because of the interface contract, and the TCK we implement as well, because without a TCK specification is useless. We can talk each other directly. So if I want to consume a database of Reactor driver, for instance, using Spring and the Spring repository from Spring Data, and I want to scale out, I will call the Akka distributed system because it's a nice distributed system behind. And if I want to throw that away in a WebSocket or server-side event pipeline, I will call Ratpack because they implement as well the reactive stream already. And if I want to create metrics, if I want to monitor my application using historics, for instance, from Netflix, I will use RxJava in that case, and I will send some data into RxJava. So this is the thing we dreamed to between TypeSafe and Netflix and the Ratpack guys. We dreamed to do this kind of thing, and now we have this tool. I'm glad because I don't want to reinvent the wheel. I'm creating bridge every time. So that's very convenient, to be honest. And it's only a set of 4 interfaces, basically. You have publisher, subscriber. There are 2 more interfaces called subscription, which is the message passing part between a publisher and a subscriber, and the processor, which is both a subscriber and a publisher. It just extends both interfaces. It's all described in a single document. It's all in the TCK as well. We implement the specification. You see the interface is not really complicated. The publisher has a subscribe method to accept a subscriber. Subscriber has 4 signal methods reacting on 4 different states. Subscription is just something you receive when you subscribe to cancel at some point or start requesting the next number of elements. So it's very useful to bind to do batch processing. For instance, you want to process 100 by a 100 element, you will request on next, for instance, 100, every time, and you can do batch processing like that. So I'm going to just conclude on a few things, in fact. The on-error, so the signal flow is really simple. What happens when you subscribe to a stream is simply described in that slide. It can be either your flow is already on error and the only event you receive is an error event, or if it works nicely, you start receiving the subscribe event, and then maybe 0 to n next event, so the data coming through you. And maybe at some point, because it's possibly bounded, a complete signal, or if something happens, you will receive error signal. And the async boundaries can be completely flexible. So there are a few patterns. If you want to have a different thread for each operation, you can do that with Reactor. You can do that with Akka Stream and RxJava as well. So 4 resources, for instance, 4 threads different for each operation. Or you can do that as well for just the head of the stream. If you want to do that on the same thread because you want to save resources, you can do that as well. It's super flexible. So I think, well, I think it's a bit over time to show you a bit of the thing, but I want to just, to be a bit more concrete and finish on something nice, and after that we go to lunch. The thing you can do with the specification, and I encourage you to discover and to play with that, you can have all these technologies playing nicely, it shows I'm propagating the back pressure nicely, and I encourage you to also discover Ratpack, which is based on Netty. It's a kind of Node.js, simple Node.js, but you can bridge all these technologies each behind the other and consume in a reactive way when the data is present, and if your subscriber, in that case, a consumer, which is based on RxJS, a very interesting framework based on reactive extension as well. If this starts being slow, well, the whole chain is going to be naturally scaled down. And you, RabbitMQ, basically won't start dequeuing messages and will hold messages if your subscriber, your WebSocket connection is slow. And this flow is very interesting for intensive reactive and real-time application we have more and more nowadays. Map, showing on the map things appearing, showing graphs, showing stats, this kind of thing. So the conclusion of that is, if you want to try, there are a few players already around, so as mentioned, Reactor, Akka Stream, and RxJava, Ratpack. Of course, these slides are going to be online, so you don't have to rush to note these things. I encourage you to read the site as well beyond the specification to understand more the driver behind reactive-streams.org. Very interesting explanation of the reactive streams specification as well. And that's basically it. Thank you.